AP Chemistry. This is the next lesson in the kinetics unit, and it's on reaction mechanisms. So a reaction mechanism is a series of steps that a reaction follows to get from reaction to products. So for example, the reaction 2NO plus O2 produces 2NO2 does not happen in one step. The reaction consists of two steps. Step 1, NO plus NO produces N2O2. And then in step 2, the N2O2 produced in the first step combines with the O2 to produce 2NO2. N2O2 does not appear in the original reaction, but it appears as a product in step 1 and is consumed as a reactant in step 2. This is called an intermediate. Each of the individual steps in a reaction mechanism is called an elementary step. So let's start with this reaction. H2O2 plus 2H plus hydronium ion plus 2 iodide ions will produce I2, an iodine molecule, and 2H2O. It has been experimentally determined that the rate law for this reaction is rate equals rate constant times concentration of H2O2 times concentration of I minus. Again, you can only determine that experimentally the way we did in the first lesson of this unit. The rate mechanism has 3 elementary steps. So we're going to write each and the rate law for each step. So the first step is to take the H2O2 plus one of the 2 iodide ions, and that produces HOI plus a hydroxide ion, OH minus. And you see the rate law on the right is rate equals K1. That's because it's the rate constant for step 1 only, but times the concentration of H2O2 times the concentration of I minus. Now let's go to step 2. The hydroxide that was produced in step 1 plus another one of the hydronium H plus ions combine to form water, H2O. And you can see that the rate law for that is rate equals K2 times concentration of hydroxide times concentration of H plus. Finally, step 3, the HOI that was produced in step 1 is combined with the other H plus ion and the other I minus ion to produce the final products, which is I2 plus H2O. And now if you look at the overall reaction up above, there's 2 H2Os. That's because you're going to add the H2Os in step 2 and step 3 together to get 2 H2O. That's Hess's law. All right, now you notice another thing, that all of the reactants that are in each of the elementary steps are used in the rate law of the elementary step. So in step 1, H2O2 and I minus are both used in the rate law. For step 2, OH minus and H plus are both used in the rate law. For step 3, HOI, H plus, and I minus are all used in the rate law for step 3. But the overall reaction up above, you notice that the overall rate constant doesn't necessarily have all of the reactants in it. It doesn't have to. So that's a distinction between overall reactions and elementary reactions. So here's a key point. For an elementary reaction, you can use the coefficient of the reactants as the exponents in the rate laws. So think about that statement. Let's read it again. For an elementary reaction, you can use the coefficient of the reactants as the exponents in the rate laws. Remember, we learned earlier in this unit that you must determine the exponents for the overall reaction experimentally. So again, if you look at step 1, it's got a coefficient of 1 in front of H2O2 and a coefficient of 1 in front of I minus. So those are the exponents in the rate law of step 1. In fact, all of the coefficients and all of the reactants in all 3 steps are 1. So you'll notice that the exponents for all of the concentrations in the rate laws are all 1 as well. Continuing with the reaction on the preceding slide, the rate law is, as we saw, rate equals rate constant times concentration of H2O2 times concentration of I minus. The rate mechanism has 3 elementary steps, and we saw those already. There they are. So the rate law, you'll notice this is a key. The rate law of the slowest step, the slowest elementary step, is the rate law for the overall reaction. And when you think about that, that's logical. An overall reaction can't happen any faster than its slowest step. So you can see that the rate law of the overall reaction is the same as the rate law for step 1. This means that the speed of step 1 is limiting the speed of the reaction. And really, to be more specific, it's not that it's step 1, it's that it's the slow step. The rate law of the slowest elementary step is going to be the rate law of the overall reaction. Again, the overall reaction can't happen any faster than its slowest step. Step 1 is the slow step, and this is called the rate determining step. The molecularity of a reaction refers to the number of molecules that participate as reactants. So unimolecular, one reactant is involved. Okay, so this would be a decomposition reaction of some sort. A produces B plus C. So there's one reactant, that's unimolecular. Bimolecular means there's 2 reactants involved. So in this case, this is a composition or synthesis reaction. A plus B produces C. And they can both be the same, by the way. It could have been A plus A produces something. Okay. And finally, termolecular. Ter means 3. 3 reactant molecules, A plus B plus C produces D. So this is a key point. For elementary reactions only, you can use the coefficient of the reactants as the exponents in the rate laws. Remember, we learned earlier in this unit that you must determine the exponents for the overall reaction experimentally. So you can see that the exponents in the rate laws do equal the coefficients of the reactants. So this down below illustrates this point. So there you have a unimolecular reaction. So the only reactant is A. So the rate law would be rate equals K times concentration of A. And the coefficient in front of A is 1, so it's to the first power. If it's bimolecular with 2 A molecules, A plus A, you can write that as 2A. So that means the rate law would be rate equals K concentration of A squared. So the coefficient in front of the A, the 2A, becomes the exponent in the rate law. If it's A plus B, it's going to be rate equals K concentration of A concentration of B. If it's A plus A plus A, this is the equivalent of 3A. You could write that as 3A. So the rate law is going to be K concentration of A to the third power. If it's A plus B, then it's going to be 2A plus B. So that's going to be K, rate equals K concentration of A squared B. And A plus B plus C will be rate equals K concentration A, concentration B, concentration C. So the key point is that the coefficient in front of the reactant is the exponent in the rate law. So compute the rate law for the reaction without using experimental data, but using the rate mechanism shown for the reaction below. So there's the overall reaction. So step 1, you're going to take one of the N2Os and break it into N2 plus O. Then in step 2, you're going to take the other N2O and you're going to take the O out of step 1 and combine that to produce N2 plus O2. Okay, so the rate law for step 1 is rate equals K1, that's the rate constant of step 1, times concentration of N2O. And since the coefficient in front of N2O in step 1 is a 1, then the exponent is a 1. For step 2, you've got 2 reactants, N2O and O. So the rate is going to be K, that actually should say K2, concentration of N2O times O. Now you see that the first one is called the slow step and the second one is called the fast step. What does that mean, slow and fast? It just means that the first step goes slower than the fast step. It doesn't have any specific speed to it, it's just slower. And this is something that you will be told in a problem, in a kinetics problem. You're not ever expected to figure out what is the slow step. Okay? And so you'll be given slow step, fast step. So you see, we use Hess's law. We cancel the O's. One of them's on the left side of the arrow, one's on the right in step 1 and step 2. And so now on the left side of the arrows you have 2 N2O, and on the right side you have 2 N2s, and you have 1 O2, and that equals the overall reaction up above. Since the first step is slow, its products N2 and O immediately become reactants for step 2. Well, actually the O does. And for step 2, the overall reaction is completed. The rate law for the overall reaction equals the rate law for the slow step, step 1. So the rate equals K times the concentration of N2O. Now you notice that the exponent on that rate law is a 1, N2O to the first power. That's because the coefficient in front of N2O in step 1 is a 1. It is not the 2 in front of N2O in the overall reaction. Again, you cannot use the coefficients in an overall reaction as the exponents in the rate law. So you'll see that the rate law for the overall reaction is equal to the rate law of the slow step. The overall reaction cannot move any faster than the slowest step. So for the overall reaction, the coefficient of the reactant is not the exponent in the rate law. That's for the overall reaction. A rate mechanism with a slow final step creates a complication shown in this example. Compute the rate law for the reaction without using experimental data, but using the rate mechanism shown below for the reaction. So here's the overall reaction. 2NO plus Br2 produces 2NO-Br. So step 1, you take those 2 NOs and you combine them to produce N2O. And so the rate law for that first step, K1, will be NO plus NO can be treated as 2NO. Okay, just think about it, just like algebra. NO plus NO is 2NO. So that means in the rate law, the NO is going to be raised to the second power because it has a coefficient of 2. And we're going to say that's the fast step. That's something that you have to be told. Okay? Now step 2, you're going to take the N2O2 from step 1, combine it with the Br2, and that's going to produce 2NO-Br, which is your final product in the overall reaction. So writing the rate law for that, you have N2O2 and Br2. So the rate is going to be K2, that's the equilibrium constant for the second step, times N2O2 to the first power, because the coefficient in front of N2O2 in step 2 is a 1, and Br2 to the first power because the coefficient in front of Br2 is 1. And that's going to be the slow step. Again, you have to be told that. Okay, so the N2O2 are intermediates. They cancel out. It's produced in the first step and consumed in the second step. And that gives you, using Hess's law, the overall reaction that you see up above. The rate law for the overall reaction equals the rate law for the slow step. That's what we said in the last slide. Okay, so that would be K2 times concentration of N2O2, concentration of Br2. But we will call this the temporary rate law for the reaction. So the rate law, temporary rate law, is the rate law of the slow step right there. But there's a problem. The temporary rate law includes an intermediate, N2O2. The final rate law should only include reactants in the overall reaction, NO and Br. So let's take a look at that reaction one more time. The overall reaction has only NO and Br. It does not have N2O2 in it. So the overall rate law cannot have N2O2. So that's our problem that we need to resolve. So for this reason, we need to find a way to express N2O2 in terms of the actual reactants in the overall reaction, which are NO and Br2. So step 1, NO plus NO produces N2O2. So we can treat that like an equal sign. So the easy way to do this is to treat the double arrows as an equal sign. This means that we can write N2O2 equals NO plus NO. And NO plus NO is 2NO. So NO is a reactant in the original overall reaction, so we can use 2NO in our final rate law. We cannot use N2O2 because it's not one of the original reactants. So we can substitute NO squared for N2O2 in the temporary rate law. So there's the original temporary rate law that we wrote on the previous slide, and that now becomes rate equals K NO squared Br2. So you see how the N2O2 was substituted by NO squared. The second equation contains only reactants in the overall reaction NO and Br2, so this is a valid rate law. A catalyst speeds up a chemical reaction without being part of the reaction. A homogeneous catalyst exists in the same phase as the reactants, example liquid-liquid or gas-gas. So there you see an energy diagram, reactants, the energy level of the reactants is over there on the left, and then it goes up over the energy hill and comes down to the energy level of the products, which is lower in this case. So that would be an exothermic reaction because it released energy to go from the higher energy of the reactants to the lower energy of the products. However, it has to go over that energy hill. You have to put energy in to break up the reactants before they are put together as products and go to lower energy. So for a catalyst to work, it must do at least one of the following. 1. Increase the number of collisions of reactant molecules. 2. Lower the activation energy for the reaction EA. So that's the top of that hill. It has to lower. So you see that with the catalyst, the purple line is with the catalyst. The green line is without the catalyst. So since the energy it takes to make that reaction happen is lower for the purple line, for the catalyzed reaction, then the reaction will happen faster. It doesn't change the beginning or ending energy of the reactants and the products. It just makes the reaction go faster. So the reaction pathway shows the activation energy, the highest point on the curve, is lowered in the presence of a catalyst. The beginning and ending energy levels are not changed. All right, so that takes care of this lesson on reaction mechanisms, and you'll be given a lot of problems over the next few months to practice these, and they will begin to seem very easy.